Welcome to Corpstruction, a show about the missions, activities, and employees of the Tulsa District U.S. Army Corps of Engineers. Today, I'm coming to you from the FEARS Laboratory at the University of Oklahoma in Norman, Oklahoma. I have with me Dr. Royce Floyd, who's a professor here, and Omar Yadik, who is an undergraduate student here, right? Can you talk about what you all do here at the laboratory?
So here at FEARS Lab, we do primarily structural engineering and concrete materials research. And all of our work is intended to try to create structures that perform better, that last longer, that, can survive better in the, ever-changing climate of this world, as well as, better serve the people, of the U.S. and elsewhere. And there are about 5 or 6 professors that work out here doing different types of research. We've done structural steel research. We've done reinforced concrete, pre-stressed concrete. But, to kind of describe it in a nutshell, we build structures, we break them, we see how they perform, and try to use that to do things better.
And one of the tests that we just watched that Omar here was working on, you guys were adding pressure to a concrete beam. And can you talk about what that was, Omar, like what you guys were doing? Just talk on that. Yeah.
So basically this is one of the projects that's been happening for the past 7 years. This beam was out there for 7 years for corrosion purposes for studies. We're basically trying to see how the beam would fail, what kind of failure mode would happen to this beam. So this test is basically we put pressure or load on the beam, and we'll try to see if there will be some bonding failure, or is going to be flexural shear failure or shear failure. And I think Dr. Floyd, you can maybe talk more about it in terms of the research.
Yeah, so there are a lot of bridges in Oklahoma, especially, that are reaching the end of their design lives, you might say. So they're 40, 50 years old. And a lot of those bridges have damage at the ends of the beams that result from, being out in the weather for all that time, for de-icing salts coming through the bridge deck onto the ends of the beams. That causes the reinforcement to corrode. When reinforcement corrodes, it expands. It spalls off the concrete. So it blows chunks of the concrete off the beam. And we wanted to see how that type of damage to the beams affected the strength, over the life of the bridge. And kind of the inspiration was just driving around and seeing this on the beams. And a student and I went to about 20 bridges or so across the state that we had identified as being from that time period. And we saw these same things over and over again. So we then put together this plan to build some replica beams that are scaled down to about half the normal size. And then to expose them to that kind of an environment with very aggressive conditions for different time periods. And so we started with beams that didn't have any damage associated with them. So they were basically, right out of the factory. Then we had ones that we had exposed for 3 months, then 6 months, then a year, then 3 years. And then the ones we just tested had been out there for 7 years. And so we were trying to, get different conditions along the life of, say, a bridge. And, we found some really interesting things. And it seems like there's some point where a little bit of corrosion at the end actually helps us get a little more strength. But then once we lose enough of the concrete, that starts to go down. And we, wish we had, 3 or 6 or 10 more of these we could test so we could find exactly where that point would be.
And you guys can build your own beams here, right?
So we have the facilities here to do fairly large scale concrete construction. And these beams were pre-stressed beams, which is typical for bridge girders. And we have a pre-stressing setup here at FEARS Lab that we can do up to 6 pre-stressing strands at a time. So we can get a pretty good scale size beam. We can never build a full size beam, but we can build small scale specimens to test in the lab.
So, and you said that the corrosion actually adds some strength at least on the front end, right? But on the back end of that, there's a different issue.
There's a lot going on there, especially when we're corroding reinforcement that's under tension, like in these pre-stressed beams. But for the specific failure mode that we were examining, which is shear in the end region of the beams, it's often controlled by the strands pulling out of the concrete. So the strands have to be anchored into the concrete to, act as a composite, to work together to resist the loads. And by loads, for a bridge, that would be the trucks going over it. But when we tested the undamaged beams, those strands just pulled away from the concrete. And that was the failure mode. As we started to corrode the beams, it seemed to take more and more load to pull those strands away from the concrete. So it was almost like the corrosion on the strands was maybe providing a little bit better anchorage between the steel and the concrete. But then we've tested some full-size beams that were, 45, 50 years old, and we saw that, with pretty extensive damage, that actually happens earlier than what it does for an undamaged beam. So somewhere in between, the 7 years we've tested and the 45, 50 years for out in the field, that original increase in strength turns into a net decrease.
Oh, and can you talk about how you simulated?
So for these specific beams, we placed them outside. We had a tub of water that we had mixed in about 5%, just table salt by weight to get a chloride solution. And then we would use a pump to just spray water onto the ends of the beams, like, say, a bridge deck joint was leaking onto them. That's what we were trying to simulate. But we just had, a aquarium pump to a perforated hose that would spray water on the end of the beam for, say, 30 minutes. Then the pump would cut off for a long enough time for the beam end to dry, and then it would start over. And it just did that over and over again for, several years. And, we would have to fix the pumps occasionally, but it worked pretty well.
Now, Dr. Floyd, the way I came across you was working on the Eufaula Bridge project, which is still ongoing with the ultra high performance concrete. Can you talk about how you got involved in that?
So this specific bridge, I can talk probably more about ultra high performance concrete than you would want to hear. But, for this specific project, it kind of goes back several years. And I had worked on ultra high performance concrete, or UHPC, when I was a PhD student. And then when I moved to OU, we started doing some small stuff in the lab. We went after some various funding opportunities. And we got a project from the state DOT to develop some UHPC materials using, raw materials you could get in Oklahoma. And so we worked on that project. We looked at, several different possible uses of UHPC, both, the stuff you can buy from the manufacturers as well as locally developed materials. We did, bridge deck joints that are similar to the ones on the Eufaula Bridge, but they're intended to be expansion joints. And actually, the Eufaula Bridge is going to have some UHPC at the expansion joints, very similar to what we were doing with ODOT. So, we were working on that project, and we did a demonstration here at Fierce Lab that I think David and Jeff, so David Jarvis and Jeff Roberts, came down to the lab and participated in our demonstration, went to the seminar that we did. And that started this discussion about the Eufaula Bridge that Jeff was working on. And it happened that ODOT has a program where they can, get some of our research expertise into specific problems that they have pretty quickly. And so we applied for that program with Walt Peters, one of the engineers at ODOT, to allow us to be part of that project at Eufaula to provide, some input, answer questions that anybody had. Also just to be on site for ODOT as kind of an observer. And it's been a really interesting project to work with that fits in really well with a lot of the work that we've been doing in the lab. And so since that first project that those guys came out to see, we've done some bridge connection testing here at Fierce Lab with UHPC. We've done some additional material development here. And one of the most interesting projects we've done recently is actually related to the beams we were testing today, where we were looking at, could we repair one of these damaged ends with UHPC? And unfortunately for you guys, we finished those tests up a couple months ago, but we had damaged beams very similar to the damage you saw today. We encapsulated those ends with UHPC, and then we retested them, and we saw that we could actually increase the strength significantly by using UHPC as a repair material.
So you can patch concrete with it and potential. I mean, do you get the same strength as before? Like, I mean, before it broke, or?
Well, so for the test that we did, where we encapsulated the entire end with about 1.5 inch thick to 3 inch thick, coating, you might call it. So it was a little bit more extensive than a patch, but we actually saw a 40% increase in the strength compared to what the original beam could do, which surprised all of us a little bit, but was a very exciting finding.
Oh, wow. So the implications on that are potentially that, I mean, you could use this to strengthen bridges that are, or materials that are in use at some point. I mean, potentially.
That was our objective, and these results seem to indicate that would be possible. And obviously we need more work to get there, and we're still working on getting those results published. But it was very promising to begin with. Kind of like the joints on the Eufaula Bridge. Use UHPC, and we can create a stronger joint material than the surrounding concrete. We're kind of using that same concept for a repair. And using the fact that UHPC bonds very well to the conventional concrete.
What are some of the other types of testing you can do with here at the lab?
So we can do I won't say just about anything you can imagine, but we've done all kinds of things where we've built our own test setups. So, within reason, the sky's kind of the limit. But the stuff we do most often is we do a ton of concrete materials testing. So compressive strength, modulus of rupture, elastic modulus of concrete, all of the hardened concrete tests. Right now we're running creep tests on some specialty low shrinkage concretes. So we do a lot of that kind of work. We do a lot of beam tests, so we can with our strong floor and our existing load frames, we can set those up to routinely do up to about 400,000 pounds of load on beams. We've also been able to do some column tests by turning those columns sideways, laying them down on the floor and loading them laterally. So we've done some really large scale column testing. We've been doing fatigue testing on concrete slab joints, primarily using UHPC, but using some other materials as well. So we've got setups to do those. We have faculty members that do dynamics testing, so using some shake tables that simulate earthquakes. He's doing a lot of work with isolation systems right now, so he does a lot of those types of tests. We can do tension and compression testing on just about any material that you can think of outside of concrete. And then we have we'll say geotechnical lab that's housed down here that has facilities to do up to almost full-scale retaining wall testing. So those are kind of the things that we do a lot right now, but we just hired a new faculty member who's working with fiber reinforced composites, and so she's setting up a laboratory to fabricate those, to do testing on that material. So we're constantly expanding our capabilities. And then we also, can build new setups as we, see fit. We have a technician that can machine new test setups. And so we've, imagined new ones, built them, and used them, over the course of a project lots of times.
So you're only limited by your imagination and whatever resources you have available, right?
Yeah, we're often limited by the capacity of our overhead crane or the largest hydraulic cylinder that we have. But even then, we can use what we know about leverage and mechanics to increase the capacity of our hydraulics by using a lever arm or whatever, as long as we can fabricate the pieces that we need.
And and what you all do is so important to infrastructure projects. Probably not only statewide, but potentially regionally and nationwide, because you were talking earlier about how the data and the information, the things that you learn here in the lab, you end up using that data to make recommendations, to make changes, right?
Right. So, we, as academics, our goal is to learn new things because we like to learn new things, and because, no one knows what those things are yet, right? So we're kind of pursuing knowledge almost for the sake of knowledge. But as engineers, we want our knowledge to be used for things. And, most of us sit on, technical committees for code development and things like that. And so we, use the knowledge that we have gained in doing research to try to change how things are done in, say, the concrete industry, to improve the way that bridges are repaired, or to, improve the way that they're built. And so we try to use that expertise and that data to move forward new technologies, new ideas, or, potentially to fix things we were doing the wrong way for a long time, which, we don't find too many of those, but occasionally it can happen.
And I mean, the implications are huge. I mean, when you look at the nation's got aging infrastructure that it's going to have to be replaced or updated or upgraded at some point, right? And if you can, in your lab, figure out ways to extend the life of infrastructure projects, or even, new projects, it certainly makes it more cost effective and potentially more safe, right, for the general public.
Yeah, exactly. And, it's not, I tell people I do research on concrete, and they kind of roll their eyes and they're like, "You do what?" And I always tell people, try to get home from wherever we are without using concrete. And it's one of those things that is everywhere, that we use to do, anything, and is especially, an integral part of the nation's infrastructure. And, there's always, some problem that needs to be addressed. And, there are a great many faculty studying these problems across the country, and working together, we have the ability to address those problems.
Right. And you are all looking at each other's research papers and data and journal articles and everything to share that knowledge. You were talking about how you tell people that you study concrete, and I mean, it's really amazing because, it may not touch every aspect of your life, but you probably touch it in every aspect of your life, right? Like, you don't think about it because you walk on it, right?
Right. Yeah.
Why do you enjoy the lab here, working in this environment?
So I really enjoy working with the students. You're constantly working with new students, which, as you're trying to accomplish research project objectives, can be frustrating at times. Because you're constantly training the students to run the tests or to collect the data or whatever. But that's the purpose of our being here. We're here to train students. And so, you're teaching the students as you're doing the work.
What other projects are you guys working on here?
So
I guess it's generated by the students a lot of times, right?
So sometimes it is generated by the students. My PhD student is working on a project that is, something he's kind of come up with the majority of, the research, our working together to identify what's the best approach, but he's looking at rapid setting cement concrete. So concrete that can gain strength in 2 hours instead of a month, and using it specifically for pre-stressed elements. So, if we can gain strength much more quickly, we can potentially increase our production rate. That's a good thing, right? But this material also has less shrinkage, less creep, which are, concrete terms for things that reduce our, say, pre-stressing force in a beam and can cause us some design issues over time. And so he's investigating, how that behavior works on a material level so that we can make better predictions to do design of elements with this type of concrete. So it's an application where it hasn't been used before. We're, examining design of ultra high performance concrete connections to make precast beams continuous for live load. So we did some laboratory tests a couple of years ago. We're doing a project now to take that data into design recommendations. We're looking at service life design for UHPC link slabs, which are slabs connecting two bridge spans that aren't really intended to make it continuous, but to keep the water out off of the beam ends. I'm working on a couple other projects that are related to UHPC joints right now. And then I have a student that's working on some different fiber types to use in UHPC, potentially to get better performance or to provide more options for, users of the material. And then also, we're trying to find ways to reduce the cost, but that's kind of less of an initiative than just trying to get the performance that we need.
And will you be going back out to Eufaula to visit the bridge project? Or?
We are planning to go back out there at some point, at least to, check on, we'll say, performance of the mock-up as well as to see how the joints that they've cast come out.
Hey, I really appreciate it. You got a great lab here, and I really appreciate you giving me the time to come out here. And Omar, I'm going to finish up with you here in a second. I'll give you a couple minutes to talk about, what you're hoping to accomplish in your career as an engineer.
Well, I appreciate you giving us this opportunity to kind of showcase what we're doing and the lab down here. And, stay tuned for all the cool things we hope to do in the next few years.
Yeah, I'm sure it's going to be great. And how many students do you typically have come through your program here?
Oh, that's a good question.
In a semester, maybe.
Man. So I usually have 4 to 6 graduate students that I'm working with, usually a few undergraduates. So 2, I have 2 right now. I've had as many as 5 or 6 in a semester that work specifically with me. And then, my colleagues that work out here usually have about the same number of students. So we'll have, 10 to 15 graduate students out here often working. They're not all here at the same time. And then, several of the undergraduate courses have labs that do things out here. So our Concrete 1 students come out here and build beams and test them. Our steel students come out here and test some steel connections. And, those classes are 50 to 60 students. So, we'll have, I would say somewhere between 60 and 80 students that'll be in and out of the lab every semester.
Wow. And one last question before I let you go. What would you say to a high school senior or junior or sophomore who's thinking they might want to be an engineer at some point in their life, particularly in your field or your discipline within the field? What would you say to them to consider it, or what do they need to do?
So that's a good question. And what I would say to any high school student is, engineering takes a lot of math and science background. So if you think you want to be an engineer, you want to be sure to take those classes to prepare yourself for success in the program. Because when you get into the university, you're going to have to take a lot of those classes as kind of the background. If that's the kind of thing that you really enjoy, so if you like math and science, engineering is probably a good pathway for you to follow. And with saying those two things, an engineering degree of any kind is a great thing to have because there's so much flexibility with what you can do. You may get into it and decide, I don't like designing things. Well, maybe you're going to be a manager or a
project manager.
Project manager, or be in construction, or start your own company. Like you'll have a background that you can do almost anything that you can set your mind to in any engineering discipline. And being that I'm a civil engineer and then a structural engineer, we're a little bit different than some of the other engineering disciplines because our focus is more on the things that make a society function. So clean water, roads and bridges, structures that people live in. They are, not necessarily as exciting as rockets that are shooting to Mars or, new microchips for iPhones. Like all that stuff's very exciting. But, civil engineers do the things that make people's lives better, but aren't always as obvious. So, if that's the kind of thing that you enjoy, so, if you want to save the environment, civil engineering is a great field to be in. If you want to, help people have clean water in other countries, civil engineering is a great, thing to be in. If you want to help people get from place to place, civil engineering is a great discipline to be in. But any engineering has, great benefits to people and to that student, a solid career path of one way or another.
Yeah, you guys are in the business of solving problems and finding solutions to the world's toughest challenges, right?
Yeah, I mean that's honestly a great way to describe engineering. It's we're solving problems, and we like to think we're solving the greatest problems that are out there right now.
Yeah, there are a lot of great people who have definitely kept up and maintained the infrastructure that helps make our lives relatively easy in the modern world, right? So thank you again, Dr. Floyd. I appreciate you taking the time to speak to me and talk to the audience and let them know what you're doing here at the University of Oklahoma.
You're welcome.
Where in Oklahoma are you from?
So I'm not from Oklahoma, actually. I'm from Jordan, and it's a country in the Middle East. I don't know if you know about it. It's where we actually have Dead Sea, Petra, the cool stuff back there. And yeah, I came here for my undergrad, and I'm right now currently studying architectural engineering, and this is going to be my last semester before I go to do my master's. So.
And do you intend to go back to Jordan, or are you going to stay here in the U.S.?
I mean, at some point, yeah, I will definitely go back to Jordan, and it's basically one of the reasons why I've been studying engineering, and I'm trying always to kind of go back at some point, try to improve the infrastructure there as a civil or architectural engineer, and because it's still developing. It's a developing country, so it's very good for me as I kind of want to give back to my society and community to go back and help to see how can I improve the infrastructure, the structures, and how to, even since I've been doing a lot of repairing stuff, how to repair current structures back there in Jordan.
And you'll start your master's here as well?
Yes, hopefully.
Okay. And that's like a 2-year program, right? So
I'm part of the accelerated master's program. So it's a year long. Sometimes it can go to like a year and a half instead of a year. So I had that option to do when I was in my junior year. I decided that I want to continue my master's because I feel as an architectural engineer, just taking the bachelor is not always enough. Especially if you want to like help in creating new materials, new methods in construction. So this is when I realized I want to enroll in the accelerated master's program here at OU.
Now, why did you want to be an engineer? When you were a little kid, did you decide, or?
So that's actually kind of a funny story. At the beginning, I wanted to be an architect. So back home, being an architect is basically being an architectural engineer. But then when I came here, I realized that those are two different things. Which I was glad that I did architecture engineering because it kind of opened my mind to the civil engineering industry and being interested in the structural engineering, because I believe in like the construction industry is growing rapidly these days. And what was Dr. Floyd basically saying about how it's growing rapidly and we always have to find new improvements and development. So trying to find more sustainable methods and materials is basically my long-term goal. As we all know that the climate change is not actually going any slowly. So it's us, the civil engineers or engineers in general, to try to find new methods in order to kind of minimize our effect to the environment and make sure that we're using more sustainable methods. So this was one of my main reasons why I wanted to be an engineer.
How old were you when you thought?
So I was in 11th grade actually when I decided that I want to go into that path and not anything else. Especially especially in the like architectural, civil engineering industry. This is when I was like, yeah, I wanna be in that field.
What are the differences between architectural engineering versus architecture in general?
So architecture, which what they call them architects when they graduate, it's basically more that you actually design the floor plans of of the structure that you're working on, it trying to make it aesthetically pleasing more than the engineers, and sometimes it's more focusing on the aesthetics than anything else. And there are a lot of great architects, and that's why,
like Frank Lloyd Wright,
yeah, and Zaha Hadid as well. So there are a lot of them, and like when you go around like in Oklahoma or even like somewhere else in the States or even internationally, you see all those crazy buildings and crazy shapes, which is very impressive, you know. But then architecture engineering is basically what helps to make it happen, you know, because sometimes you can design some crazy shapes and beautiful shapes, but then are they actually going to be practical in real life? And that's the main question as architectural structural engineer we ask ourselves. So this is the main difference. Architectural engineer focuses more on how to make those designs happen and on the whole structure, such as mechanical aspect of the structure, electrical, lighting, and also the structural aspect of the building, of course.
So while I've got somebody here from Jordan,
Yeah.
I'd be stupid if I didn't ask. What is the building material typically in Jordan compared to say here in the United States or Oklahoma in general?
You know, you would find it funny. It's quite different actually, because back home we have literally almost no wood structures. You know, so when I came here to the States and I saw all those houses, all those sometimes like big buildings that they actually use wood as as the main material for that building, I was really surprised, like how using wood is actually efficient, like in real in life, you know, because back home we mainly use concrete and masonry, and that's it. And maybe because we don't have enough forests back home to use wood, but yeah, this was the main difference between like in terms of materials back home and in the States.
And in Jordan, I would imagine probably the type of wood that is available is probably, I mean, might be great for carpentry, but might not be the best for holding up a house or whatever. Or
yeah, basically that's another reason we don't have we don't have the resources that the United States has in order to be able to design wood structures. So
and I guess even roofs, right? Like the shapes or the incline.
Yeah, so back home
the
also
grade.
yeah, back home most like roofs are almost flat. I mean, there's obviously some slope for drainage purposes, but then they're like flat and that's it. But then when I got here, they're all like, you know, those like roofs, like the inclined roofs and like all those angles, and like even like in terms of talking about like houses structures, it's very very different. Like here, having those roofs is very different than what I was used to back home, and it's a different experience for me, obviously. And it was kind of it was very interesting at the beginning, but then once you get used to it, right now you can start like kind of like connect to two different kinds of structures, if that makes sense.
What about roads?
So what do you mean by what about
Is it
roads?
generally
Like,
the same type of concrete material? Or
Oh,
I
no.
know here we use a lot of paving and pavement.
yeah, so basically back home we use a lot of asphalt. We don't have any concrete roads per se. Yeah, like also here in the highways, when I see like some sections with like concrete, I'll be like, like I've never seen this before. And back home it's always asphalt, and that's it. That's the main material for roads.
And is it relatively flat? Is that part of the reason, or is it?
No, actually, it's quite the opposite. In Jordan, it's not flat at all.
Okay.
It has a mountainy environment, so you can find a lot of uphills, downhills, up and down, and like that's the difference between Oklahoma, for example. It's quite flat wherever you go, basically.
Well, in your part of the state, it is. Where
Oh,
you're living.
maybe. Maybe I haven't been that exposed
Oh, yeah.
to
You need to come
Oklahoma.
out east.
Oh, really? Okay.
Yeah.
I'll try that for sure
Yeah.
then.
There's a reason they call it green country.
Oh, okay.
Have you had a chance to? So you were out at the Eufaula Bridge project with Dr. Floyd. What did you take away from that experience?
So it was a very great experience for me because I started working for Dr. Floyd in January 2021, and I've been dealing with a lot of like projects or like civil projects in terms of UHPC, and we analyze them, we test them as well, but I've never seen an application in real life. So when the first time I went with Dr. Floyd to Eufaula Bridge project, I was very interested to see how that material can actually work in real life, especially with also a larger volume of UHPC, and how the heat will affect the flowability of the concrete, and whether it's gonna be working in terms of bonding with the conventional concrete. So there were like a lot of different aspects in my mind that I wanted to take out of that experience, and it was great for me to go there in the mock-up, and also in the first cast of the actual bridge. So those are some of the things that I took out of that experience, and hopefully we'll be back also again to kind of oversee and test the mock-up and see how it's actually behaving in terms of like joints.
Yeah, I know the like in other typically that prior to this even the bridge was tensioned, right?
Mm-hmm.
So and now with that UHPC they're not going to have to use that process to lay those panels and connect the panels. So that will be pretty interesting to see. Like, I mean, was that the first time you'd seen the UHPC as opposed to just tensioning?
In actual like applications, yes,
Mm-hmm.
This was the first time for me. But then yeah, that would be very interesting to see and observe how it's gonna behave, because as you said, it's gonna be basically the only connection between the deck panels. So that will be something interesting to observe.
Did you get to take a look at the sort of the skeleton structure below on the other side?
Oh yes. That was very, very interesting as well. Like going and like seeing all those different like stuff.
Mm-hmm.
It was fun. It was definitely a great experience, learning experience especially.
Yeah, there's a lot of pretty big dams here in Oklahoma. I mean, some of those. Have you had a chance to visit any of the lakes or any of the other lakes in Oklahoma since you've been here?
Yeah, I've been like in Thunderbirds, Hefner, Crystal Lake as well, but not that many. And Eufaula Lake right now, obviously, I can add it to the list.
Yeah. Well, how are you finding? So you've been here 4 years? Is that about
4 years? Yeah,
4 years here. You started here as a freshman, came in, and were you right out of high school or?
Yes,
Okay.
but I wasn't. I did not finish my high school in Jordan.
Okay.
I finished it in Bosnia.
Oh, okay.
Yeah,
Wow.
and
What was
it's
that like?
oh, it's it's a honestly for me it was one of the most beautiful experiences because it's an international school and has different campuses around the world. It's called the United World College, and I lived in Bosnia for 2 years, finishing my international baccalaureate IB, um, and in that school we had more than 60 nationalities and 200 students bodies. So that means that the students were literally from all over the world. So it was the first time that I got that much of an exposure of different backgrounds and cultures, and collaborate in like different projects with other students from completely different backgrounds. So
How many languages do you speak?
me, I speak two languages, Arabic and English.
Arabic and English.
Yeah.
You didn't learn what's the language in Bosnia?
Bosnian. I just learned the basics just because I had to deal with some locals at some point. So I just learned the most basic stuff. But yeah.
Uh, uh, that's really amazing. So you've traveled quite a bit.
Yeah. I've that's also one of the reasons why I got interested more in the engineering industry and also the architecture, because like when I traveled around and I did like a semester where I actually went to 13 different countries in 4 months, I I saw different architectural styles and how it can actually convey some of the culture of that country, and also to observe the different methods that they use in every single country in terms of construction, and to see the different infrastructures in each country and how it's different, for example, than the States as well. So this was also one of the other reasons why it got me more interested in being a structural engineer than any other kind of discipline.
Yeah, and from the part of the world where you grew up,
Hmm.
people travel a lot between the different countries there, right? Between what Jordan and Syria and I mean, well, you're close to Iraq and right,
Yeah,
and
yeah,
so what are the 13 countries you've been to, or can you name some of them
yeah. Yeah, I
aside
can.
from Bosnia?
Bosnia, yeah. So I went to Japan, South Africa.
Oh,
Uh,
you didn't even drive; you flew.
it wasn't. It wasn't actually flying. It was more like on a ship.
Okay.
I spent like 4 months on a ship, studying. It was a study abroad program, but then I went to different countries, and while we were traveling on the ship, we used to study and do all that kind of fun stuff. But then, yeah, I went to Japan, China, Ghana, South Africa, Morocco, India, Vietnam, Myanmar. Yeah,
Wow.
yeah, and
Southeast Asia and Asia
yeah. We
as
covered
well.
we covered mainly Southeast Asia, very south of Africa, and then all the way to Europe. So,
What were the roads like in Vietnam?
oh, like we went to Ho Chi Minh City. There, the infrastructure in general was pretty impressive, to be honest. Like the roads were nice, were flat, and all the infrastructures for in terms of like bridges, also transportation, were very impressive. Honestly, like I did not have any kind of idea before going to Vietnam, and when I went there as an engineer, I was looking through. You always look for those kind of stuff whenever you go. It's part of few at this moment, so it was mainly asphalt as well. I couldn't see a lot of like concrete roads, but then also most of their structures, concrete and masonry as well, and the wood was very minimum. So that's why it got me also interested more in the heavy use of wood in the States other than anywhere else. So
Wow, that's just amazing. It's always interesting to meet people who've traveled, especially not. I mean, and you traveled even outside the Middle East where you grew up too. So I mean, that's just amazing. So, Well, hey, thank you for your time, Omar. Is there anything any advice you would give to a student who, or someone in high school, or who wants to be an engineer?
Yeah, I can. I mean, I can try to give an advice
From your experience.
Yeah. So, based on my experience, honestly, if you're good, if you're really into science, math, and trying to be a problem solver, and you have good creativity in terms how to solve problems in different ways, try to think about engineering as like any kind of discipline, honestly, because it really makes you think on how to improve and develop the world that we live in, and it's an essential thing to do as people. We always try to improve and develop, and more things that engineers do is in like computer science or like mechanical or like civil. We always try to find new solutions for every single problem, and it happens throughout your whole career. First of all, you won't get bored of any kind of routine when you work, because you always have different projects with different environments. So it will just also, again, requires a lot of creativity and problem solving skills. And I would advise you, if you have those things and you're ready to have some intense undergraduate experience, go with engineering. And if you're interested in civil engineering, it's even better, because this is basically how what everything starts. We start everything. We make it easier for any other engineer to build whatever they want to build, like ships, rockets. Without us, they won't be able to do any of that thing. So
the foundation, quite literally, right?
Basically, civil engineers and all its disciplines are is the foundation of any other kind of discipline. I mean, my opinion.
Well, hey, Omar, I really appreciate your time. Thank you for sitting down and talking to me and sharing your story about. That's just outstanding. Hey, have a great day, and best of luck with your master's program, which is going to be here before you know it, right?
Yeah. Thank you so much, and thanks again for coming here and explore our Fears Lab. So.
Yeah, and you'll be able to see Omar if you watch the YouTube video that we post with this podcast. You'll actually be able to see Omar in there assisting and helping out with the project. Thanks again, Omar.
Thanks, appreciate it.
Thank you for joining us for Corpstruction. Corpstruction is a production of the Tulsa District U.S. Army Corps of Engineers Public Affairs Office. To learn more about the Tulsa District U.S. Army Corps of Engineers, visit us on the web at www.swt.usace.army.mil. You can find us on most social media sites at USACE Tulsa, all one word. Have a great day.